Have you ever stopped to wonder why some chemical reactions are just faster than others? I mean, really, why do some things happen in the blink of an eye while other things take forever?
Think about it. An explosion is just bam, it's over in a flash. But then you have something like a piece of iron rusting, which can literally take years. They're both just chemistry in action, so what's the deal? What's controlling the speed limit for these reactions?
Well, it turns out there's a kind of recipe, a really powerful formula that chemists use to figure all this out. It's called the rate law, and it's pretty much the cornerstone of understanding reaction speeds. So let's take a look.
Okay, here it is. Rate equals K times A to the M, B to the N. Now I know it looks a little mathy, but trust me, every single part of this equation tells a crucial story. You've got the rate, this constant K, and then the amounts of our reactants, A and B, each with these little exponents, M and N. Today, we're going to unpack this whole thing, piece by piece.
So here is our game plan. We'll start with the basics, what rate and concentration actually are. Then we'll dive into those mysterious little exponents M and N. We'll meet the rate constant K, and then for the main event, we're going to solve the puzzle of its units, which is really the key focus of this whole explainer.
All right, let's start with the absolute fundamentals of our recipe, the speed of the reaction itself, and, how much stuff we're actually mixing together. It's actually pretty simple when you think about it. The rate is just how fast things are going. The reactant concentration is how much of each ingredient you put in the bowl to start with. They're obviously related, but, and this is key, they are not the same thing. In chemistry, we have to be super specific about speed. The rate is literally the change in concentration over a certain amount of time. And its standard unit, you're going to want to remember this, is molarity per second. M/S. That unit is our anchor for everything else we're about to do. And concentration, which you see with those square brackets, is measured in molarity, just a capital M. That's just a way of saying moles per liter, basically how crowded the molecules are. So let's lock this in. Rate is M per second, concentration is just M. Got it? Because these units are about to become very important. Okay, now for the really cool part. Those exponents, M and N, are like the special instructions in our recipe. They tell us how much each ingredient actually matters to the final speed. These are called reaction orders, and they basically tell you how sensitive the reaction speed is to each ingredient. If you change how much of something you have, the order tells you exactly how the speed is going to react. And let me tell you, some ingredients are way more influential than others. And this is where it gets wild. Look at this. If a reactant is zero order, meaning its exponent is zero, you can dump in as much as you want and nothing happens. The speed doesn't change at all. Kind of weird, right? Now, if it's first order, it's a one-to-one deal. Double the ingredient, double the speed. Simple. But second order? Oh, this is where it gets fun. You double the concentration and the rate quadruples. That's a huge jump. Now, please listen to this. This is the biggest trap people fall into. You cannot, I repeat, cannot just look at a balanced chemical equation to find M and N. It feels like you should be able to, but it's a trap. The only way to find these orders is by rolling up your sleeves, getting into a lab, and actually running the experiments. And this table shows you exactly how that works. Let's say we want to find the order for NO. We look at experiments 1 and 2, because see how the O2 amount stays the same? That's the key. You only change one thing at a time. So the concentration of NO doubles. Now look at the rate. It jumps from about 0.028 to 112. That's a 4-fold increase. So we doubled the concentration and the rate quadrupled. What does that tell us? The reaction is second order for NO. That's how we find it. So we've got our ingredients and we've got the special instructions. Now we need to talk about the oven temperature, the thing that sets the overall pace for the whole recipe. And that's the rate constant, K. So K is just a specific number for a specific reaction as long as you keep the temperature the same. You can just think of it as a measure of how fast the reaction naturally wants to go. A bigger K just means a faster reaction. Simple as that. Okay, this brings us to the central puzzle. We know the rates units are always M per second, and concentration is always M. So, what are the units of K? Well, here's the crazy part. They're not always the same. The units of K actually have to change and adapt depending on the reaction orders, just to make sure all the math works out.
So let's solve this puzzle. We have all the pieces. I'm going to show you exactly how to figure out the units of K for any reaction you come across. The very first step is just a little bit of algebra. You take the rate law equation and you just rearrange it to get K all by itself. So you end up with K equals the rate divided by all the concentration terms. Remember, we're not solving for a number here. We are just hunting for the units. Let's walk through an example. Say we have a second-order reaction. First, we get K by itself. So K equals rate divided by concentration squared. Now we just plug in the units we already know. For rate, we put in m over s. For concentration squared, we put in m squared. Okay, so 1m on the top cancels out 1m on the bottom. And what are we left with? A 1 on top and an m times s on the bottom. So the units are 1 over m dot s, or m to the minus 1, s to the minus 1. See? It's just a little unit cancellation game. And using that same method, you can basically build yourself a handy little cheat sheet. For a zero-order reaction, the units of K are just m/s, same as the rate. For first order, it's 1 over s. For second order, it's m to the minus 1, s to the minus 1, and so on. You can totally see the pattern here. And there you have it. Once you break down the rate law into all its parts, the rate, the concentrations, the orders, and that tricky rate constant, you've unlocked the entire recipe for reaction speed. You don't just know what the pieces mean, you know the very units they're built from. But that leaves us with one final, really interesting question. We said K is constant at a constant temperature. So what happens if you turn up the heat? Or what if you add a catalyst to the mix? The rate law is fantastic at telling us how concentration affects the speed. But it turns out the biggest secrets of all are hiding inside that little constant K.